everyone, it's Leanne. I'm going to talk about problems for section 1. So this is chapter 4, section 1, or 4.1, and you were assigned 1 through 5 and 8. And so what I'm going to do is, for every section that you were assigned problems, I'm going to go through and explain possible answers. So I'm going to explain my answers. Some of them will vary from what you did, but for the most part, you can use that to see if you're correct or to help you if you were a little bit confused about what the problem was asking. So I'm really hoping that this is helpful, and let's go ahead and get started. All right. In the first one, because we did what did we do? 1 through 5 and 8. Yep, so in the first one, we are using this section's definition of multiplication. So m times n equals p. So the number of groups times the number in each group equals our product. And we're using that definition of multiplication to explain why these following problems can be solved by multiplying. So A, B, and C. So let's go down to my work here. So in the first one, we had that there are 3 feet in a yard, and if a rug is 5 yards long, how long is it in feet? Well, we're going to view our our yards as groups and our feet as objects. And so each yard is a group of 3 feet. Let me get my pen going here. And so we have 5 equal groups with 3 feet in one group. So by definition of multiplication, we can simply do 5 times 3 equals 15. In the second one, there are 5,280 feet in a mile. How long in feet is a 4-mile stretch of the road? So in this case, we're going to think of each mile as a group. Sorry, I erased that word, of 5,280 feet. And so we have 4 equal groups, with each group having 5,280 feet in that one group. So by definition of multiplication, we'll do 4 times 5,280 to get our answer, our product of 21,120 feet. All right, in the third one, Will is driving 65 miles per hour. If he continues driving at that speed, how far will he drive in 3 hours? So in this one, each hour is the same as 65 miles, and so we're looking at having 3, that should say, equal groups with 65 miles in one group. So there's our 3 equal groups, 65 miles in one group. So by definition of multiplication, we're going to do 3 times 65 to get 195 miles. All right, in 2 through 5, you had to write your own problems, and you're writing your own problems to basically practice using our definition of multiplication with a variety of different contexts. So an array word problem, an ordered pair word problem, a multiplicative comparison word problem, and then we're also going to include a strip diagram. And so what we're going to do, I'm going to read the problems that I wrote and just talk about them briefly. You can use that hopefully to help you determine if what you did was on track as well. All right, so number 2 is asking us to write an array word problem for 6 times 8, and then to also explain why the problem can be solved by multiplying 6 times 8. And so I wrote this. A kindergarten classroom has 6 equal rows where there are 8 cubbies in each row. And so we can multiply, and so then how many cubbies are there? That's our question. So we can multiply 6 times 8 together in this example, because in each row is one group of 8 cubbies. So there are 6 equal rows, and in each one there are 8 cubbies. So there are 6 groups of 8 cubbies altogether. All right, in the third one, we're asked to write an ordered pair problem for 6 times 8. So here is the ordered pair problem I came up with. A couple had a baby, and they had 6 first names and 8 middle names picked out. So how many different pairs of names are possible, assuming they're only going to use 1 first name and 1 middle name? So this is a problem for 6 times 8 because we can multiply 6 and 8 because each first name, gives us the first part of the ordered pair, which corresponds to the rows in the array problem up here. And then each middle name gives us the second part of the ordered pair, which corresponds then to like the columns, if you think of it that way, from number 2. And so we have 6 groups of 8 names. All right. In the fourth one, we are asked to write a multiplicative comparison problem for 6 times 8. And so I wrote that there are 8 cookies in a small box, and then that there's also a big box that has 6 times as many cookies as the small box. And so you can see that I'm comparing size here. And then the question then would be how many cookies are in the big box. So this works for our interpretation of multiplication because the big box contains 6 equal groups of the small boxes, or 6 equal groups where there are 8 cookies in each group. So there are 6 times 8 cookies altogether. All right, in number 5, it's also a multiplicative comparison problem, but this time we had to draw a strip diagram and kind of rewrite the problem. So the problem that I wrote here is that there are 5 ants in Griffin's ant farm, and then Tabitha's ant farm has 3 times as many ants as Griffin's. And so the question is, how many ants are in Tabitha's ant farm? And so to draw a strip diagram, I want to draw that there are 5 ants. I want to draw a strip to represent Griffin, and then I want to show a strip that represents Tabitha. And I think you're going to find by the end of this semester that the strip diagram is a super helpful way of looking at not just multiplication problems, but also ratio problems and even some algebra type problems. So here we have, we have Griffin's ant farm, and I don't know how I just moved that over. We have Griffin's ant farm, and he has 5 ants, and then this strip represents Tabitha's ant farm, and she has 3 times as many. So you can see that the strip, the visual representation or the math diagram, corresponds to the verbiage in this problem. And so then you're asked to write the same problem, but this time reword it so that we are using 1/3 in the statement. So I rewrote it this way: Tabitha's farm has 15 ants, because now we're going to rewrite the problem looking at how many ants would be in Griffin's ant farm. See how I switched it there? So Tabitha's ant farm has 15 ants. Griffin's ant farm has 1/3 as many as Tabitha. So how many ants are in Griffin's ant farm? All right. And the last one here is number 8. Number 8 is kind of a long problem. We're looking at John, Trey, and Miles, and we want to know, they want to know how many 2-letter secret codes that there are that don't have a repeated letter. So for example, they want to count BA and AB, but they don't want to count doubles like ZZ or YY. So John says that there are 26 plus 25 because you don't want to use the same letter twice, and that's why the second number is 25. He's onto something there, but Trey thinks it should be times, not plus, 26 times 25. Miles says the number is 26 times 26 and then minus 26 because you need to take away the double letters. So you had to kind of think about this problem, discuss it, and decide who is correct. So I'm hoping that I can explain my answer here. All right, so Trey and Miles are correct. John is not correct. We're not adding in this case, we're multiplying. So Trey and Miles are correct because they both calculate 26 times 25 combinations. They do it a little differently from each other, but they're both calculating 26 times 25 combinations. So here's why. Think of it this way. So you have 26 choices of the first letter. Since you don't want a repeated letter, you have 25 choices for the second letter. And each of the 26 first choices is a group. So for each group, there are 25 second choices that correspond to the 25 2-letter codes for each group. So if we go back to our definition of multiplication, we know that 26 equal groups with 25 in one group gives us 26 times 25. Miles, and that's kind of what Trey was thinking. Miles is also correct because he's making all the combinations, 26 times 26, but then he's subtracting out the 26 combinations that would result in like a double letter, and so that result will end up being the same result. All right, so that is 1 through 5 and 8, and I hope that explanation helped you guys. Thanks for watching.